Okay, so in this video, we want to consider the concept of a basis of a space of vectors. And let me explain why I'm saying that a space of vectors and not explicitly Rn. As we will see in this video, we can consider subsets of Rn, such as say a line passing through the origin, or a plane passing through the origin in R3, of course Rn itself. But we will soon, in the next few videos, extend our concept of vectors to more general objects. We'll consider any rectangular M by N matrix as a vector, and we'll even consider functions as vectors. So just keep this in mind that what we'll talk here about Rn and its subsets will apply to more general sets of objects, which we'll call vector spaces. So here's a definition of what a basis is. So let V be a space of vectors. So again, V could be, say, a line through the origin, or plane through the origin in R3, or Rn for any n. But later on we'll see that V can even be more general than that. It can be a space of rectangular matrices, it can be a space of functions, and so on. But for now, think of V as being Rn, or a subset of Rn. So let V be a space of vectors, and B be a subset of V. So B is a set that contains, say, m vectors, v1, v2, up to vm, and all these vectors are contained in the space of vectors V. Right? This notation means is a subset of. So B, the set of these m vectors, is a subset of V, the space of vectors, which means every element in B is an element of V. Therefore, every vector in our set is a vector in the space of vectors V. With this now, we can define what a basis of the space of vectors V is. So we say that B is a basis of V if B satisfies two conditions. So if condition A, the elements of B are generators for the entire space, and therefore generate means taking all possible linear combinations, therefore the span of the vectors in B, so the span of these m vectors, has to be the entire space. Right? The span of a set of vectors is the set of all linear combinations of these vectors. And B will be a basis if the span of the vectors in B gives you the entire space of vectors V. So if A, that's our first condition, and B, the vectors in B are linearly independent. And these are the two conditions to say that B is a basis of V. And now, again, what is a basis? Well, condition A says a basis is a set of generators for the space of vectors, right? If you find all linear combinations of these m vectors, you get the entire space. So the vectors in B generate the entire space, but the idea is, again, we want a set of generating vectors for the space to be as small as possible, right? And think of this, if you can generate the space, say with 4 vectors, why would you use, say, 5, 6, or more? It doesn't make sense. You want to generate the space with as few vectors as possible. And that's what condition B guarantees. If the vectors are linearly independent, then we know that none of the vectors will be linear combinations of the others, and so you do need all of these m vectors. So if you lose one of those, you will actually lose part of your space. So condition A again guarantees that the set of vectors in B generates the entire space, and the fact that the vectors are linearly independent guarantees you that the set of generators you have is as small as possible. Let's consider, let's say, 3 examples. We'll consider an example for Rn for any n, then for a plane in R3, and then we'll look at 2 new definitions regarding rectangular matrices, which will give us 2 new subspaces, spaces of vectors. Let's do one example. So consider Rn for any n, and you'll see that we'll have a very simple and yet fundamental basis of Rn for any n. So Rn is the space of vectors with n components, the space of vectors of length n, so x1, x2, up to xn. And again, the xi's, x1 through xn, range over all possible real numbers. That's what Rn is. Well, again, let's split those n components, and we'll get a linear combination. If you factor in x1, you will have x1 times the vector 1 and everything else 0, plus, if you factor x2 times the vector now 0, 1, and everything else 0, up to xn, plus xn, factoring xn out of this vector, times the vector all zeros and the 1 at the very last entry. Where each xi can range over all real numbers. And if you look here, what we have is the span of these n vectors. We have x1 times this vector plus x2 times this vector up to plus xn times this vector. And because x1 through xn can range over all real numbers, we have here the set of all linear combinations of these n vectors. And this is by definition the span of these n vectors. So the vector 1, 0, 0, all the way down, the vector 0, 1, 0, all the way down, up to the nth and final vector 0, 0, 0, 1 at the very end. And we give these vectors very special names. We call this vector E1, we call this vector E2, up to, this is the nth one, the vector En. And these are very simple vectors to describe, right? If in general, Ei, the ith vector, will consist of all zeros except for the ith entry, which will be a 1, right? E1 is all zeros, but the first entry is 1. E2, all the entries are 0, but the second entry is 1. Up to En, all the entries are 0, except the nth entry is equal to 1. So now we have a set of generators, right? The set E1, E2 up to En spans all of Rn, so this is a candidate for a basis, right? The first condition for a basis must be that the span of the vectors is the entire space of vectors. And our space here is Rn, and indeed the span of these n vectors is all of Rn. But there is one last condition we have to check. The vectors must span the space, which they do here, but the vectors must be linearly independent. Well, why is this obvious here? Well, remember that vectors are linearly independent if the only way to obtain a zero vector through a linear combination of these vectors is the trivial solution. Therefore, if you construct the linear system, the reduced echelon form of the matrix will be so that every column will contain a leading one. Therefore, every variable is leading, which implies a unique solution. But think of building the matrix where the columns are E1, E2 up to En. This will build I. And therefore, every coefficient of the linear combination will have a leading one, which implies that all variables are leading, therefore, a unique solution being the trivial solution. So automatically here, we also have linear independence. So indeed, this is a basis of Rn, and it's also called the standard basis of Rn. And that's our first example of a basis. These n vectors form a basis of Rn, and they're very special. They're called the standard basis of Rn. Now, one last little definition before we consider our next few examples, and that is the concept of dimension. If you recall in the previous video, we said that if we use our intuition, and if you build back from R1, just a real line, the dimension we think of it as 1. If you think of R2, the xy plane, we think of it as having a dimension equal to 2. If you think of R3, the xyz coordinate system, we think of it as being a three-dimensional space. So in general, because Rn consists of all vectors with n components, and every entry could be anything you want, we think of Rn being an n-dimensional space. And if you see here, Rn is spanned by n linearly independent vectors, and so we'll now define this, but the dimension of a space of vectors is simply the number of elements in a basis. So you can see here, if we say, well, what is the dimension of Rn? This will be the number of elements in a basis. This happens to be n. So the dimension of Rn is exactly n. Let's define this more generally, and then we'll just prove very easily that a basis of Rn has to always contain n linearly independent vectors. So this definition makes sense. No matter which basis of Rn you choose, and no matter which one I would choose, we will always have exactly n linearly independent vectors. So let's define the dimension properly and then write down what we've just said about Rn. So if B, a subset of V, is a basis of the space of vectors V, then we denote and define the dimension of V by the following. We write simply as we did before, dim for dimension of the space of vectors V, and all this is the number of elements in any basis that you find. Let's now prove that this makes sense and is well defined in Rn, but we will prove later on, when we consider more general spaces of vectors, that this is always true. If you have a space of vectors, even where the vectors may be rectangular matrices or even functions, if you find one basis and I find another, they will always have the same number of elements. Therefore, this definition makes sense. Let's now make a remark about Rn. Sorry about that. So any basis of Rn must contain exactly n linearly independent vectors. So if I give you a set and I ask you, is this a basis of Rn? If you have fewer than n vectors or more than n vectors, you don't have to do anything. Guaranteed it cannot be a basis because a basis for Rn has to contain exactly n linearly independent vectors. And think of why that is, right? There are two conditions for B to be a basis of Rn. The vectors in B must be, condition B, linearly independent. And now we're assuming that it is the case. But the vectors in B must also span Rn. And think of it. Vectors will span Rn if when you put them in a matrix and you row reduce the matrix, you get exactly n leading ones. But think of it. If you have fewer than n vectors, then you will have fewer than n leading ones. Therefore, the vectors will not span Rn. So you have to have at least n vectors. But if you have more than n vectors, now think of it, you will lose linear independence. If you have more than n vectors when you row reduce, since you only have n rows, that means that one column will not have a leading one. Therefore, you will have at least one free variable, therefore an infinite number of solutions. Therefore, the vectors will be linearly dependent. So you see, if you have less than n vectors, you cannot span Rn, but if you have more than n vectors, the vectors are dependent. So the only way to have a basis of Rn is to have exactly n linearly independent vectors, which proves that the dimension is well defined because any basis of Rn will contain exactly n vectors, and so the dimension of Rn is equal to n. Let's consider now a simple example of a plane passing through the origin in R3, and we'll ask to find its basis and the dimension of this space of vectors. So this is our second example. So find a basis, and again, there are many bases, and bases is the plural of basis, but given any space of vectors, there's always, or almost always, an infinite number of different bases. So find a basis and the dimension of the plane, we'll call this plane pi, and just to make it simpler, we'll take 1 times x as the first term. Let's go with plus 6y minus, let's go with minus, not that it really matters, 9z is equal to 0. So we have this plane in R3, and again, it is a plane passing through the origin because the origin, the point 0, 0, 0, is a solution to the equation. Replace all x, y, and z by 0, and it solves the equation. So this is a plane passing through the origin. We want the basis for it and the dimension of the plane. Well, let's see. Every time you look for a basis of any space, that means that you have to describe the space explicitly. Well, here what we have is implicit, right? We're told that the points on this plane are the solutions to this equation. What are the solutions? Well, we have to find them explicitly, therefore we have to solve the linear system. As you will see though, this will be quite easy to solve because it already will be in reduced row echelon form. So we can write the solution set. Y and z are free, so you can let y be, say, s, z be t, and x will be negative 6y plus 9z, therefore negative 6s plus 9t, where s and t range over all real numbers. Now think of it. We write the points on this plane, or vectors, right, because points are vectors and vectors are points, as a column matrix, x, y, z. So the points on the plane must be of this form for some choice of s, some choice of t. So negative 6s plus 9t, s and t. Split the free variables, s and t, and you will get s times negative 610 plus t times 901. And if you look now, every point on our plane is a linear combination of these two vectors. Some multiple of this vector plus some other multiple of this vector. And because s and t can range over all real numbers, we see that the span of these two vectors will give us every possible point on the plane. Therefore, the plane is equal to the span of these two vectors. Negative 610, 901. We can call this vector v1 and this vector v2. Sorry. And now we have the first condition, right? A basis of a space, and the space here that we consider is the plane in R3. So we have a subspace of R3, right? This plane is living inside of R3, but clearly is not the whole space. So it's a subspace of R3. And we now have two generators, right? The span of these two vectors gives us the entire plane. So a question is now, do we have a basis? Well, a candidate would be taking the vectors v1, v2. And B will be a basis of pi, the plane, if, first condition, the span of these vectors give you the whole space, which we have just proved. So these vectors are generators of the plane. And the second condition is the vectors must be linearly independent. Well, remember what we have proved in an earlier video. Two vectors are linearly dependent if they are parallel, if one is a multiple of the other. Well, is v1 a multiple of v2? Well, if it were, 0 would be equal to a multiple of 1. Well, what times 1 is 0? That's 0. But 0 times v2 clearly is not v1. These two vectors are not parallel, so clearly they are linearly independent because neither is the 0 vector. So let's write that down. So since we only have two vectors as generators, and they're not parallel, and keep in mind this argument only works for two vectors. If we had more vectors, we would have to look at the matrix, row reduce it, and make sure that every column contains a leading one. But because we only have two vectors, no need for it. And because they are not parallel, the vectors are linearly independent. So we have a basis. The vectors in B span the entire space, and the vectors in B are also linearly independent. So we have our conclusion. B is a basis of pi. Well, we also asked, and of course the vectors here are negative 6, 1, 0, 9, 0, 1, but of course we also asked for not only a basis of pi, but the dimension of pi as well. Well, recall our definition of dimension. Given a space of vectors V, the dimension of the space is the number of elements in any basis. Well, we have our basis here, so the dimension of the plane, which is our space of vectors, will be the number of vectors in a basis, and we have here a basis with 2 elements, so we get a dimension of 2. And this fits perfectly with our geometric intuition of a plane, right? A plane in space, no matter where you put it, is a 2-dimensional flat surface. So this matches our intuition perfectly. Let's consider now 2 more definitions, which will give us 2 examples of subspaces of Rn. And these will be subspaces that will come from fixing a rectangular matrix. So here's our definitions, and here's the setup. We let A be a fixed M by N rectangular matrix. And recall that we can view a matrix as a function, right? We can view the matrix A as a function from Rn to Rm. If you take a vector, and you can check it here, if you take a vector in Rn, say x, so again a column matrix of length n, so if this is an n by 1 vector, a column matrix of length n, and you multiply the vector by A, where A is a m by n matrix, this is the action of the matrix. We take points or vectors in the space and we multiply them by our matrix A. First of all, is Ax defined? Well, n equals n, check. The multiplication between A and the vector x is defined, and the result is a m by 1 vector, so a column matrix of length m. So this does belong to Rm. And now with this idea in mind, we can form one subspace of Rn and one subspace of Rm. Let's first define the subspace of Rn. This is called the kernel of matrix A. And the kernel is quite simple. So we write usually K-E-R for kernel of A. It's the set of all vectors in Rn, all vectors x, that satisfy one property, and the property is the vectors in the kernel of A are the vectors are sent to the 0 vector in Rm by the matrix A. So the property is if you multiply the vector x by A, you will get the vector in Rm, but we only take those where A times x is the 0 vector in Rm. And that is the kernel of the matrix. We also have the image of matrix A. And we denote this by Im for image of A. And this is simply every possible vector in Rm that are of the form A times x. So we just multiply every point of Rn by A, and that's the image. It's just multiplying every point of Rn by the matrix A. Well, if you remember, if you were to write the matrix A one column at a time, multiplying by a vector of length n, what you will get is all, and this you should check as an exercise, this will be simply the set of all linear combinations of the columns of A. So this will be the span of the columns of A. And that's what the image is. And if you think of it, well, A is an M by N matrix. The columns have length M. So they are vectors in Rm. And if you take the set of all linear combinations of vectors in Rm, you will get vectors in Rm. And that is exactly what the matrix A times Rn is. And this will be a subspace of Rm. So it's worth noting, right? This is a subspace. The kernel of A is a subspace, a subset of Rn. But the image of A will be a subspace, a subset of Rm. Just for good measure, let's just check this. It will take us 2 lines, and then we'll consider an example of a matrix, and we'll find its kernel, a basis, and the dimension of it, and we'll also find the image as well. Let's just prove this. So we have our matrix A, which we said was an M by N matrix. So it will consist of N vectors, right? There are N columns. So the matrix A will be, say, column 1, column 2, up to the nth column. And now if we multiply a vector in Rn by this matrix, let's see what we get. We'll have matrix A, V1, V2, up to Vn. And we are multiplying vectors in Rn, therefore column matrices with n components, say C1, C2, up to Cn. And we know from the sheet on linear combinations that if you multiply a column matrix, a column vector by a matrix, what you will get is simply the linear combination of the columns of A, where the entries of your column matrix are the coefficient. This will be C1 times V1 plus C2 times V2 up to Cn times Vn. And because we're multiplying all of Rn by A, the coefficients C1 through Cn can take on any real value of your choice. Therefore, A times Rn gives you all linear combinations of the vectors v1, v2 through vn, and this is the span of the vectors v1 through vn, therefore the span of the columns of matrix A, as we have claimed. So now let's do an example. Let's take, say, a 2 by 5 matrix. We'll find its kernel, its image, the dimension, and a basis for both in both cases. So let A be equal to, say, 2, 3, 4, negative 5, 8, 2, 3, 5, 4, and say 10. And the size is important, right? This is a 2 by 5 matrix. So the matrix A will be a function from R5 to R2. Let's find the kernel, and then we'll find a basis for it and a dimension, and then we'll move on to the image. But you will see that once we do the work for the kernel, we'll actually have already have done all the work for the image as well. Okay, so the kernel of A, remember, consists of all the vectors in R5. Let's write this explicitly. So vectors with n components, say x1 through xn. So x1, x2, x3, x4, x5. But we only keep those vectors that are killed by matrix A. So A times the vector equals the zero vector in R2. And again, it's easy to check because this is a 2 by 5, this is a 5 by 1. The result will be a 2 by 1 matrix. So it is the 2 by 1 zero matrix in R2. And that's your kernel, right? The set of vectors in Rn that are killed by matrix A. So once you multiply the vector by the matrix A, you get the zero vector, in our case in R2. But now think of this equation. This is A times X equals B, right? So think of what we have here. The kernel of A consists of the vectors of length 5 that are solutions to the equation AX equals B. So we're just looking at finding all solutions to this linear system. So we can write this, of course, as an augmented matrix, and the solutions of our system will be the elements in the kernel. So in a sense, there is really nothing new here. And as always, whenever you look for a basis, you have to solve for the elements of your space explicitly. And here what we have is implicit. The vectors in the kernel are the solutions to this linear system. Well, you will never find a basis unless you actually find the elements of your space explicitly. So here we have to solve this linear system. So x1, x2, x3, x4, x5 are the variables. The constant terms are 0. And the matrix of coefficients is the matrix A. So 2, 3, 4, negative 5, 8, 2, 3, 5, 4, 10. Well, first operation, before we multiply this by a half, let's do row 2 minus row 1. And we'll get 0, 0. 5 minus 1, 5 minus 4, 1. 4 minus negative 5, 4 plus 5, 9. 10 minus 8, positive 2. This is still 0. Now we'll multiply row 1 by a half. So we'll get 1, 3 over 2, 2, negative 5 over 2, 4. We want the reduced row echelon form of our matrix. Let's finish by doing row 1 minus 2, row 2. We are only changing row 1. The zeros will remain zeros. So we can recopy row 2 as is. One minus 2 times 0, 1. 3 half minus 2 times 0, 3 half. 2 minus 2 times 1, 2 minus 2 is 0. Negative 5 over 2 minus 2 times 9, negative 18. But negative 18, if you want this over 2, is negative 36. Minus 5 is negative 41. And finally, 4 minus 2 times 2, 4 minus 4, is 0. Now we have the reduced full echelon form of our linear system, so we can write the general solution set. We have 5 variables, x1 through x5. As always, we handle the free variables, which are x2, x4, and x5. Let's call those rs and t. And now solve for the leading variables. x3 will be negative 9x4, negative 9s, negative 2 x5, negative 2t. x1 will be negative 3 half of x2, which is r, so negative 3 half r, plus 41 over 2 times x4, which is s. And now we have the complete solution set, where r, s, and t, I'm running out of space here, but they range over all real numbers. And now from this we can write our basis. If we wanted, we could knock off these over 2's by replacing r by 2r. So if you replace r by 2r, you've knocked off the over 2 here. So you get just negative 3r. If you replace, and here be careful, there's an s here too. If you replace s by 2s, 2s over 2 is just s. And here you'll have negative 9 times 2s. This will become negative 18 times s. And this will give us a basis without fractions. And as always, if you can, try to avoid introducing fractions. But now we're good to go. We have found the elements of our space explicitly. And you'll see that once again, to get the basis, we'll just have to split the 3 free parameters. So, the elements in the kernel were the solutions to this linear system. We have found all of them, so we can replace now. x1 was negative 3r plus 41s. x2 was just 2r, sorry. x3 was negative 18s, negative 2t. x4 is 2s, and x5 was t. Let's now split up all 3 free variables, so r times the vector negative 3, 2, there's no r, no r, no r, so 0, 0, 0, plus s times 41, 0, negative 18, 2 and 0, plus t times 0, 0, as there's no t, negative 2, 0, positive 2. And look what we have now. Every vector in the kernel must be equal to this for some choice of r, s, and t. Therefore, is a linear combination of these 3 vectors. So this is v1, say. Call this v2. And call this v3. And because r, s, and t are free variables, they are allowed to range over all real numbers. Therefore, the span of these 3 vectors, recall the span is the set of all linear combinations of given vectors, But because R, S, and T are free, we do have here all linear combinations of these three vectors. So the span of v1, v2, v3 gives you all the elements in the kernel. So the kernel of A is the span of these three vectors, v1, v2, v3. So we now have here three generators. The vectors v1, v2, v3, through all possible linear combinations, give you all the vectors, all the elements in the kernel. The only question is, condition B, are these three vectors linearly independent? Right? So we have here a possible choice of a basis. Condition A is satisfied, the span of B is the whole space. We have to check now for linear independence. And this I will leave up to you, because remember, to check for linear independence, put these three vectors in the matrix, row reduce, and if every column contains a leading 1, therefore we have a unique solution, and so we have linear independence. And this is very easy to check using row reduction. If you wanted to, you could be sneaky and you could avoid the row reduction by looking at this. Because this linear combination can be collapsed into this vector, and you see, if this vector were equal to the 0 vector, well, look at this entry. T would have to be 0. Look at this entry. This would also have to be 0. Therefore, if 2s is 0, s would have to be 0. And this entry would have to be 0, but if 2r is 0, r would have to be 0. And you see, the only way that this vector equals the 0 vector is if r equals 0, s equals 0, t equals 0. But if r, s, and t are all equal to 0, and that is the only solution, by definition, these three vectors are linearly independent. So either you notice this shortcut, or even if you don't, put the three vectors in a matrix, row reduce, and check that you have in each column a leading 1. Either case, this is a basis of the kernel. So we have the dimension. The dimension of the kernel, or any space for that matter, is the number of elements in any basis, and here our basis contained 3 generators. Therefore, the dimension of the kernel of our 2×5 matrix is equal to 3. And that completes our look at the kernel. We found a basis, and we have the dimension. Let's now look at the image of matrix A, find a basis for it, and the dimension. And you'll see that we already have done all the work. If we only look at the reduced to echelon form of the matrix A. So recall that the image, so let me just rewrite the matrix A. It was the matrix 2, 3, 4, -5, 8, 2, 3, 5, 4, +10. And recall that all the image is the span of the columns of the matrix A. So it is the span of the vectors 2, 2, 3, 3, 4, 5, -5, 4, 8, 10. So right away we already have a set of generators, right? Right away, by definition of the image, it is the span of the columns of A. So we already have a set of generators. The only question is, are the vectors linearly dependent or independent? If they're independent, we're done. If they're dependent, The question is, which vectors do we throw away to reduce our set to a basis? Let's give these vectors name. This is vector v1, v2, v3, and don't confuse those as the ones we've used in the kernel, right? We call these vectors v1, v2, v3, but now we're moving on, forget this, and now we call these vectors v1 through v5. Whoops, v4 and v5. So we have 5 generators. The question is, do we need all of them? Well, we already know that they are dependent, right? The vectors are in R2. They only have 2 components. And so if you reproduce this matrix, we know that we can have at most 2 leading ones, but we have 5 columns. So at least one column will have no leading one, therefore an infinite number of solutions. Therefore, automatically these vectors are linearly dependent. The only question is, which one can we throw out and not lose anything? And the answer lies in the reduced echelon form of A. Remember the intuition. If you have a leading 1 in a column, this means that this column generates one dimension. If a vector does not have a leading 1, it generates nothing new, and you don't need it. So let's put this with what we have at this point. We have reduced the matrix A to this form. The first column does contain a leading 1, which says that vector v1, will span one dimension. So you have to keep this vector. Vector v2 does not contain a leading 1. Therefore, this second vector gives you no additional dimension, and you can just throw it out. And it's clear from just by looking at the two vectors, because look, vector v2 is just 3/2 of vector v1. So v2 is just a multiple of v1. So if you already have v1, you don't need v2. And this was already clear from the reduced echelon form of the matrix. No leading 1. This vector gives you nothing new. You can drop it and you lose nothing. Now v3 does contain a leading 1, so v3 will allow you to build to span an additional dimension, so you have to keep v3. But v4 and v5 don't have leading 1s, therefore they don't span any additional dimension, so you don't need v4 and v5. You can drop them. And now if you're left with these two vectors, they will form a basis, because if you reduce the matrix formed by these two vectors, you will get in the end these two columns. So you'll have 2 columns, 2 leading 1s, which proves linear independence, and they will be a spanning set for the image. And now you have your basis. And that's it. So the dimension of the image actually is simply 2. And if you notice here, there is something interesting. Right? The dimension of the image, is the number of elements in its basis. But the basis contains 2 vectors, therefore the dimension of the image is 2. This is a parenthesis, but this happens to always be true. If you recall, A was a 2, well, it's right there. No need to recall, but A is a 2 by 5 matrix. And if you notice, 5 is 2 plus 3. And this will always be the case. If you add the dimension of the kernel of a matrix with the dimension of the image of a matrix, it will always be equal to the number of columns of the particular matrix. And this is not an accident. Proving this is a little bit more subtle, so we'll just make this observation and we won't go any further. One last mention, or something worth mentioning, is the image of A is something very simple. If you think of it, the image of A is the span of these two vectors, but these two vectors are in R2, and they are not parallel to each other, right? And recall that vectors will span R2 if and only if the reduced to echelon form of the matrix that they give you will contain two leading ones. But, as we have just done before, if you start with just the vector v1 and the vector v3, and you row reduce, you get a leading one in each column. So, because the reduced row echelon form of the matrix 2, 2, 4, 5 contains two leading ones, these two vectors span R2. So the image of A is actually simply R2, the entire xy plane. So if you think of it, we could give now a even simpler basis for our image. Because the image is just R2, the whole of the xy plane, any basis will do, so we could give instead just the standard basis of R2, 1, 0, 0, 1. And this would also be an appropriate basis for the image, as the image is all of R2, because the basis vectors span all of R2. And now this is a simpler basis, being the standard basis of R2. And that's it.